This is fall 2024 worksheet 1. So I'm just going to go through this packet very quick. The first thing I'm going to do here is I'm going to take this formula here and I'm going to do degrees of unsaturation. This is always step 1. 1 should be find degrees of unsaturation. 2 should be find IR fragments. 3 is proton NMR fragments, and then 4 you should be trying to find any hidden fragments, and then 5 is draw all possible structures, and 6 is find correct structure. Let me do DOU below that. Okay, so that's kind of like the 6-step process I do to find these structures from all this data. So DOU is going to be equal to 1 for this, and there's a formula that you can do. Let's see if I can remember. I think this is right. 2C plus 2 minus H plus N minus X quantity over 2. And if you stuff these numbers in, you'll get the degrees of saturation to be 1. Right? This means 1 pi bond or ring. So the DOU, or degrees of saturation, is equal to the sum of the pi bonds in rings. So since it's 1, it's either 1 pi bond or 1 ring. Okay, in the IR, which is step 2, I'm going to find the useful peaks, which is going to be the carbonyl. There's an sp3ch, but that's not super important. That's just something to note. And you might want to label that in your lab class if you have IR, when you have IRs in your lab class, because you should label everything you can outside the fingerprint region in a lab class. Okay, next I'm going to go to the proton NMR and try to get fragments. And so this is a CH2, this is a CH3, and this is a CH3, and I get that from the integration. I think just for this first one, I'll do it just like your lab class, so this might be helpful for your lab class. You get this little table in your spec assignment in the lab class, and I'm only doing this just because of the lab class. And then split in couples 2, right? And so I'll just name this signal A, B, C, just to be easy. So this will be A, B, C. So A integrates for 2, because that's right there. B is going to integrate for 3, and C is going to integrate for 3. If I had to, if I wasn't given the integrations, if you see these little lines, let me just not have my Post-it note be sticky. The way I would do it is I take a piece of paper, which you should always have a piece of paper, like a periodic table or something on your exam, and I would just make a little small scale here. And of course, this is going to be 1 on that scale. And when you measure these other ones, there will be about 1.5. And then this is the same, so it's also 1.5. But you can't have half a proton, so it's 2 to 3 to 3. That's the way you would do it if you're not given the integration numbers. So the chemical shift, I'm just going to read off the x-axis. So for A, it's going to be like 4.1. For B, it's going to be 2. And for C, it's going to be like 1.3. The splitting, this is a quartet. For B, it's a singlet. And for C, it's a triplet. This, remember, you have the n+1 rule, which is equal to the number of peaks. So this quartet is going to be 4 peaks, which means that it has 3 neighboring protons. So this signal A is 2 protons on the same carbon. They're split by 3 protons on neighboring carbons. Signal B is 3 protons on the same carbon being split by 0 protons on the neighboring carbon because it's a singlet. Signal C is 3 protons on the same carbon split by 2 protons on neighboring carbons. So, since B is not being split by anything, it's not going to couple to anything. Couples 2 is what is splitting what. A is 2 protons split by 3 protons. C is 3 protons split by 2 protons. So A and C are coupling each other. If A is split by C, C necessarily has to be split by A. You can't have A split by C without C being also split by A. Those have to go together. Okay, So now I'm going to take that A and C are coupling each other, so I'm going to connect these two together, and I'm going to make these fragments. Just for space, I'm going to put my carbonyl I got out of the IR right here. Oh, I guess you can still see it there. When I was teaching discussion, the document camera wasn't as high up. So, and then I'm going to count my atoms. So that's step 3. Step 4 is any hidden fragments. The way I check for that is I'm going to count my atoms. 1, 2, 3, 4 carbons against my molecular formula. 1 oxygen and 8 hydrogens. So there's 1 extra oxygen here, and this is my hidden fragment that I don't see in the proton NMR or in the IR. Okay, now that I have all the fragments, there are not many molecules I could make here. There are actually only 2, because there's 2 end puzzle pieces over here, and there are 2 middle puzzle pieces over here. So I'm going to draw both possibilities. Which are these. Now, the way I get these structures is really by using these two things. The number of protons, unique protons, and the integration. This chemical shift and splitting are how you tell which one of these 2 structures is right. And I'm going to do that off of the chemical shift in this case. So remember, with chemical shift, things near electronegative atoms tend to have a higher chemical shift because they get de-shielded. So I'm going to look at this resonance at A, right? It's the most de-shielded. It should be nearest the most electronegative atom, and that's going to be the oxygen here. So this is the right structure because this is A, this one's B, and this one's C. Because this is at 4, this is the right structure, right? It's the most de-shielded. If B and A were switched places, that's what this molecule would look like. So just to give you a sample of what it is. So this is the correct structure for this problem. Let's move on to the next one. Okay, I'll do this one just a little bit quicker. So degrees of saturation, again, the formula's on the previous one. You should get 5 for your answer. Next, we're going to look in the IR. You get a carbonyl. Then, when we come and look at the proton NMR, I have 5 protons in my benzene region. By 5 protons, that means I have a monosubstituted benzene. Again, I'm just doing 2 plus 3, and I'm getting a 5 that way. I don't care about what belongs to what peak once I do that. Then, when I have these here, this is going to be CH2, CH2, and CH3. Okay, I got 1, 2, 3 middle pieces, and 2 end pieces. There are 3 possible structures I can have here. Now, you can solve these integration patterns and figure out which one's the correct answer. You can also, if you're very good at IR, figure out what the right answer is from the IR spectra. But the way I'm going to do it is I'm not going to do any of those because that's probably what you're used to, and you're welcome to do it that way. I have no problem with you doing it that way. But I'm going to do something, and I'm going to use the splitting pattern, the theoretical splitting patterns of these combined with integration. So when I look at these 3, what I see is this one right here, these hydrogens right here would show up as a singlet. These over here would show up as a singlet over here. This one would have no singlets in it. So already I can tell one from the other 2. But between these 2, this would integrate for 2. There's 2 protons here. But this is a CH3, it would integrate for 3. So just looking for a singlet in the proton NMR, I could tell which one of these it is. If I found a singlet and integrated for 2, it would be this structure. If I found a singlet and integrated for 3, it would be this structure. If I found a singlet or if I don't find a singlet at all, it'll be this structure. So when I look at the NMR, I see there's no singlets here. So this is the correct structure. And again, of course, you see this should be a triplet, this should be a sextet, and this should be a triplet. And you see it goes triplet, sextet, triplet. So then, in fact, all the data does match with this. This IR IR peak being below 1700 is because this ketone's conjugated to the benzene ring. I think we'll probably talk about that more in lecture as time comes on. But I'm going to move to the next problem. Okay. Degrees on saturation with this one is going to be equal to 6. Again, you can go through the formula. I'm just in a hurry, so I need to do this while I can. All right, so this is going to be 6. Whenever you have something that's 4 or more, you should immediately try to look at the benzene region. In fact, we have 4 protons in the benzene region. Now, I have 4 protons, so it's di-substituted. So it could either be ortho, meta, or para. In this case, they're a pair of doublets. Pair of doublets means you have a para-substituted benzene ring. So there's going to be something on either side. I also have a peak between like 10, 10 and a half. That 9 to 10, 10 and a half region is like an aldehyde. That's where that would show up. So I'm going to put that down as well. Oh, I forgot to put this as my carbonyl. Right? Now, I did all my IR and my NMR to give my obvious peaks. This TMS is a control. This is to just calibrate your axis. So ignore those TMSs whenever you see them in the spectra. Now, I haven't used the nitrogen yet, so I haven't used everything. But I've used 7 carbons and 5 hydrogens and 1 oxygen. So if you subtract that, I still have NO2. Oops. NO2 left over, right? So, the way that this is going to get connected, because it's para-substituted, is, and this is kind of not doing a trial by, or drawing all possible structures. This is just going to put the aldehyde on one side, and on the other side, I'm going to put NO2, like that. Now, if you don't know what NO2 looks like, it's called a nitro group, and you will get to know this very well in the semester, right? You can get NO. Negative charge, positive charge. 1, 2, 3, 4, 5 for the ring, 6 degrees on saturation. This is the correct structure for this spec problem. Okay. That one was a little bit harder. All right, resonance practice. Draw all resonance structures, resonance hybrid, box the major contributing resonance structure. So if you're not used to resonance, you definitely need to get some practice because resonance will show up a lot this semester. And then we're going to swing this. Notice that in positive resonance, the arrows are moving towards the charge, right? And then in fact, we're going to have one more resonance structure, and I'll redraw the initial structure we have here. Put our lone pairs, it's from the oxygen. Like that, right? So these are the different ones, and I'll just number them 1, 2, 3, and 4. This is 1 again, right? I just redrew 1, right? So the resonance hybrid first is just going to be like a dashed line anywhere the pi bonds were, partial positive charges anywhere there was a positive charge in your resonance structure. And then the major contributing resonance is going to be the one where the octet rule rules, which is going to be this one here. So that's almost certainly going to be, it's almost always the one where the charge is on a heteroatom. Okay, this one right here, again, I'll do the easy one here first. And then I guess I should redraw this. Swing those electrons. Notice it's one arrow and it's always going towards the charge. And then one last one, I guess, will come up. Okay, the major contributing resonance structure is going to be this one, and then the hybrid is going to look like that. There's a delta plus, delta plus, delta plus, delta plus, and delta plus. Like that. That's the hybrid. All right, now we're going to do negative resonance. Notice you're going to have 2 arrows, and they're going to be moving away from the charge. like that. And now I have to just make the resonance hybrid. Like that. Major contributing resonance structure will be this one because of electronegativity. So for these, it's the octet rule for this electronegativity. Quick rule of thumb, the charge zone is always, in the major contributing resonance structure, the charge zone is always on a heteroatom. But knowing the octet rule rules and knowing the electronegativity will give you like the tools to be able to figure out if there are multiple electronegative or heteroatoms. All right, this is just some SN1, SN2, E1, E2 practice. So this first one is a strong base, strong nucleophile with a tertiary leaving group. This is E2. I have a non-bulky base, so it's going to come and take to make the most substituted alkene. This is not E or Z because these two methyls groups are the same. Okay, this is weak base, weak nucleophile with a secondary leaving group. This is going to be SN1 plus E1. So the mechanism is going to go this way, plus, and then we're going to, if it's, let's do SN1 first. So plus, I guess it didn't ask for the mechanism, but I'm gonna just doing the mechanism for your edification. Okay, and then if I come from here and I just go straight, use a red pen. I could get my E1 product. Like that. So this is the correct structure, this is the correct structure, and then I guess you can't see that super well, but this is also the correct structure. All right, this one here, this is a strong base, strong nucleophile, secondary leaving group. This is going to be E2, right? So it's going to be this proton minus plus. Remember, sodium is a counter ion, it dissociates here, right? There's no stereochemistry shown, so you will probably also get this as a product as well, both E and Z. So this is E, this is Z. All right, H2O and heat, this is going to be E1, is going to be the major product. This is going to leave. Then we're going to get a methyl shift. Now we're going to do our elimination. Which is here. Okay. Good, that's the last problem on this. I should put a box around this. Make sure you are regularly studying your organic chemistry. This is not a class. You should be waiting until just before the exam to try to learn all the reactions. Make sure you're practicing like 30 minutes a day at least. I would encourage an hour, hour and a half a day, but at least 30 minutes. Review your reactions every day when we get to them. Know your pKa's and spend time understanding the material. Okay, this is week 1 video.